Hello everyone, my name is Rishali and for this video I will be explaining this Verilog code for a simple traffic light controller. This code is a great starting point for understanding a core concept in digital design called infinite state machine. So firstly I'll open Xilinx. This program is written in Verilog, a hardware description language used to design digital circuit. You can think it of like a blueprint for a real electronic component. So we'll start from creating a new project. I'll give a name simply traffic light 01. Okay. So we have select this HDL. Then we'll go next. Then next. Then taking a new source, Verilog module, we have to select. Then again give a simple name, something like this, traffic lights 01, and make sure that it is add to project. Then next. Then here we have uh, inputs and outputs. We have clock signal, which is a heartbeat of our circuit, and a reset signal to start things off. And output, we have red, yellow, and green signals that will control our traffic lights. So I'll get like that. Red, yellow, and green. And we'll add this input, select input, output for this. And right now I'm not using bus. Like basically, bus is used for when we have a large number of input and outputs. So right now we have less input and output. So we'll go through this. Next, finish. Next, next, finish. So this is the code, and make sure all these steps are here. Like all these steps, 7 step we have do properly. If any of this step is missing here, that then we do some mistake before going to next step. So make sure that you do all this step carefully. So now I'll write the code here. So code is a bit big, so I'll just come back after writing whole the code. So this is complete code. Now I'll explain it one by one. So from here, firstly, this is our module. Here are input and 3 outputs. So first is our sequential block. That is this part. So from this always in bracket lines, this lines tells us that this block only changes the positive edge of a clock or when the reset signal is active. This is what makes it sequential. Its behavior depends on timing. The state variable, which is 2-bit register, is our state machine. It holds the current state of our traffic light. When we activate the reset signal, the state is set to dash to dash B00, which we have decided that will represent our starting point, the green light. This is after the reset, the line state less than equal to state plus 1 dash B1. This line means that on every single clock cycle, the state value will simply increment. It cycles through the binary values 00, 01, 10, and 11, and then back to 00. This is the mechanism that makes our traffic light cycle through its states. Now, the second part is a combinational block. This one, this, its start from always to the end module. So this the always at the rate state is a line. This line is a key here. It means that whatever the state value changes, the code inside this block will immediately update the output. It's like a seed of a rule that say if the state is X, then turn on light Y. Then the state is 2-0 BB. The circuit says the green light to on 1-B1 and the other to off. When state is 2-B01, it sets the yellow light to on. Then and when the state is B-2-B10, it set the red light to on. The default case is a good safety measure to ensure the output are always defined, and here it's just defaults back to the green light. So this is the main code. Now we'll just save this. Then we'll check the syntax as our code is right or wrong. So yes, the syntax is correct. So then we'll simply go here, create a new source. We'll select here Verilog test fixture, and we can give any name. Like I'll just give test like 2. Okay, so then make sure to add to project, then next, and finish. So now here I will write a code and show you guys after a minute, explain you. So this is the code for our test bench. So the test bench is a simulation environment for our main module. It doesn't get synthesized into hardware. It's only the purpose to apply stimulus inputs and observe the response, that is output, for the unit under test. So here, register clock, register reset. Inputs the unit under test must be declared as a register because their values are driven by the test bench via red, yellow, and gray. Outputs for the unit under test must be declared as wire because their values are driven by the UUT, that is unit under test. So, so this is a non-synthesizable block that generates the clock signal. It says every 5-minute units, nanoseconds, due to time scale that's toggle the value of clock. This creates a clock with a period of a 10 nanosecond. This line initial begins. This block execute from initial begins to end. This block execute only once at the beginning of the simulation. Clock equals to 0. Initialize the clock to the known state. Reset equals to 1. States the reset signal high to bring the UUT to its initial state. This line, after 20 nanosecond delay, the reset signal is released, set to 0, allowing the traffic lights module to start its normal operation. This line, after waiting for another 200 nanosecond, the simulation is stopped. This duration is long enough to observe multiple state transition. So now we'll again save this and uh, go to behavior simulation and we'll simulate behavior model. So this is our final output. So this is the waveform output from the simulation. It's visually proves what we have been saying about the code. So look at the bottom. The clock signal is toggling, and the reset signal this uh, goes from high to low at the very beginning of the simulation. This means our test bench is working correctly by providing the necessary input signals. Now let's look at the green, yellow, and red at the top. You can see they are changing incredibly fast. Right after the reset is released, the green light stays on briefly. Then it's followed by yellow, turning on, turning on for a very short period. Then red turns on. Then the cycle repeats almost instantly. So the changes happen on every single rising edge of the clock signal. Because the typically clock runs at millions of cycles per second. This proves that the lights are flashing so fast you have never been able to see them. This simulation output is a crucial because it shows us that our design, while logically correct but not functional for its intended purpose. So to fix this, we can make a real world traffic light. We would need to add a counter. The counter would count a large number of clock cycles and only then tell the state machine to move the next state, ensuring each light stays for a few seconds. So this is our complete design for a traffic light controller from the main code. This is Testbench code, and this is our final output simulation. We can even see, just a minute, we can even see the idle schematic. The circuit diagram. This is the circuit diagram for our design, inputs and output. So this code demonstrates the core principle of a finite state machine. Firstly, sequential logic that handles the state changes over time, and second, combinational logic besides the outputs based on the current state. So, by understanding these two parts, we can begin to design more complex and practical design system. Thank you for watching and subscribe for more such video. Thank you.